On the interval 0, 1, lambda here is the spectral parameter. And 1 is the first important result was the theorem by Borg, who noticed that the potential core of the Sturm-Liouville equation can be uniquely recovered from two spectra. One spectrum is in general is insufficient, but if we have two spectra satisfying two spectra for the same equation with different boundary conditions. For example, we can choose one spectrum corresponding to the Dirichlet boundary conditions and the second spectrum corresponding to Neumann-Dirichlet boundary conditions. If we have such two spectra, then the potential is uniquely specified by them. What is important here that we have the same boundary condition at one of the ends of the interval, say at x equals 1, and at 0 we have different boundary conditions. Another classical inverse problem statement for the Sturm-Liouville equation consists in specification of eigenvalues and norming constants. For definiteness, consider the Sturm-Liouville equation with the Dirichlet boundary conditions. Then, as it was denoted on the previous slide, lambda n are the eigenvalues of the problem 1, 2. And it will be, in the talk, it will be convenient for me to specify norming constants in the following way. Let yn be the normalized eigenfunctions. It's well known that when the potential core is real valued, then all the eigenvalues are simple. So each eigenvalue has exactly one eigenfunction up to a multiplicative constant, and let them be normalized by this condition. And then we specify norming constants as the derivatives of eigenfunctions at 0. you see the eigenfunction itself at 0 satisfies the Dirichlet boundary condition, and its derivative is some non-zero number. For definiteness, we can assume that it's positive. It's well known that the spectral data, the eigenvalues, and the Norman constants uniquely specify the potential Q. This problem is equivalent to the inverse problem by a spectral function. The uniqueness theorem for this problem for the first time was proved by Marchenko in his paper of 1950. And later on, Gelfand and Levitan developed the famous method for solution for solving this problem. Actually, Marchenko and Gelfand and Levitan considered a little bit different boundary conditions, but it is not important here. For the Dirichlet boundary conditions, this uniqueness theorem is valid. And another way of choosing the spectral data for unique reconstruction of the potential is the while function. Let me introduce some notations. Denote by S and C the solutions of equation 1 satisfying these initial conditions. So S of x lambda is the so-called sine type solution, and C is the cosine type solution. I have to say that everywhere in my talk, prime denotes the derivative with respect to x. So there are the derivatives with respect to x. Since the Sturm-Liouville equation depends on the spectral parameter analytically, we get that C and S and C are entire analytic functions in lambda for each fixed x. Furthermore, lambda n's are the zeros of this function S at 1 lambda, and the second spectrum of the Borg problem, mu n's are the zeros of C at 1 lambda. Next, define the while function as this ratio. We see that the functions in numerator and denominator are entire. So the while function is meromorphic, and its poles and its zeros coincide with the two spectra of the Borg problem. At the same time, if we find the residues of the while function with respect to its poles, lambda n's, we get these numbers, squared Norman constants. So if we have the while function, we can find its zeros and poles and obtain two spectra. On the opposite, if we have two spectra, we can construct these entire functions and find the while function. And also, if we know, we can determine Norman constants, and if we know one spectrum and Norman constants, we can construct the while function. So these three sets of the spectral data, two spectra, one spectrum and Norman constants, and the while function uniquely specify each other, and each of them uniquely specify the potential. So there are three, for the second order, there are three equivalent statements of inverse spectral problems, of classical problems. Now proceed to the fourth order. My talk will be focused on two problems which generalize the mentioned classical inverse problems for the Sturm-Liouville equation to the second order, or to order 4. Here we also consider this equation on the interval 0, 1, P and Q are integrable functions. And let us consider three spectra, S12, S13, and S23, corresponding to different sets of boundary conditions. You see that at the point 1, all these boundary conditions are the same for all the three spectra. But at 0, they are different. And there are all three possible combinations of three boundary conditions for y, for derivative, and for the second derivative. And our first inverse problems is formulated as follows. Given the three spectra, we have to find the functions p and q. As far as I know, this inverse problem for the first time was formulated was first considered by Barcelon in his two papers of 1974. Afterwards, there were also subsequent papers. In the first paper, Barcelon formulated the uniqueness theorem. So he tried to prove that these three spectra uniquely specify P and Q. In fact, Barcelon considered more general boundary conditions. Oh, sorry. We considered more general boundary conditions, but we, for definiteness, choose these ones. But unfortunately, the proof of Barcelon of this paper contains mistakes, and it was unclear, at least for me, whether its results are true or false. As you can see, the journal is Geophysical Journal International, so Barcelon took this problem from some geophysical applications, and this paper actually is not rigorous from the mathematical viewpoint, and that's why the proof contains some inaccuracies. And in the next paper, Barcelon developed some numerical method for the solution of this problem, and there were also other papers by Barcelon and by other authors who studied numerical methods. But the uniqueness was an open question, actually. And the second problem, which we will consider, let me also formulate it. This problem is taken from the paper by McLaughlin of 1982. Also, there were some subsequent papers in which this problem was investigated. This problem also deals with the fourth order differential equation 3 with the following boundary conditions. Here I keep McLaughlin's original boundary conditions. Of course, some other types of boundary conditions also can be considered. Here at 0, the boundary conditions of order 2 and of order 3 are imposed. This notation is used for the quasi-derivative, which is defined in this way. And at the right endpoint at x equals 1, we have these boundary conditions, the same as in the previous slide. Let lambda n's be the eigenvalues of the problem 3, 4. For simplicity, we assume that they are simple. Then there is exactly one eigenfunction corresponding to each eigenvalue. Let us assume that they are normalized by this condition. If P, Q, and the constants A, B, and C are real valued, then the problem is self-adjoint. So always the eigenfunctions are real, and we can normalize them in this way. And you see that these eigenfunctions, they satisfy the boundary conditions at 0 with the second derivative and with the third derivative. So no, we don't know about the values yn at 0 and yn prime. We denote them by gamma n and xi n and call them Norman constants. And the problem of McLaughlin is formulated as follows: given the spectral data, the eigenvalues and two sequences of Norman constants, we have to find the functions p and q and the constants a, b, and c from the boundary conditions. Clearly that this problem generalizes, so it was some attempt to transfer the results by Marchenko and by Gelfand and Levitan to the fourth order case. What was done in the paper by McLaughlin? McLaughlin studied the solvability of this inverse problem under a condition that there exists a transformation operator. For order 4, it's a restrictive condition. It doesn't always hold. So there was some specific result about existence of solution, but there was no uniqueness theorem, because if this restrictive condition doesn't hold, McLaughlin's method doesn't work. So she didn't investigate the uniqueness of solution. And how I came to this problem, in recent years, you see that, of course, the majority of studies in inverse problem theory are concerned with the second order, with the Sturm-Liouville equation. But the Sturm-Liouville equation is already well studied, and that's why many researchers are turned to higher orders, in particular to the order 4. And I made some paper by Chinese mathematicians. I'll not provide a reference to this paper because its results are wrong. And I began a discussion of their mistakes, and they tried to use McLaughlin's results, the results of this paper, but they use not existence but uniqueness theorem for this problem. And I started to argue that the uniqueness for this problem doesn't hold. And finally, I have proved that actually uniqueness for this problem is valid, and its solution is unique. But before discussing my results, I'll tell a couple of words about transformation operators. What I mean by transformation operators. Consider some differential equation, for example, equation 3, or it can be some other equation with some coefficients. Let y be its solution, and y naught be a solution of the analogous equation with 0 coefficients. And then the transformation operator is the Volterra integral operator of this form, which transforms the solution of the trivial problem to the solution of a trivial equation, to solution with of non-trivial equation with some non-zero coefficients. What is important here, that the kernel of this operator doesn't depend on lambda. It doesn't depend on the spectral parameter. And for the Sturm-Liouville equation, transformation operators of this form played a very important role in the development of inverse spectral theory. In particular, the first results by Marchenko, Gelfand, and Levitan were obtained by using transformation operators. the famous Gelfand-Levitan equation contains the kernel of transformation operator. But transformation operator method appeared to be ineffective for higher orders, because for higher orders, representation of this form doesn't always exist, and the existence of transformation operators and the application to inverse spectral problems for higher order differential operators was extensively studied by Soviet mathematicians, Sakhnovich, Khachatryan, Malamud, and some others. So they comprehensively studied this question, and they obtained some results for higher order, but all these results are concerned with analytic coefficients or piecewise analytic. For example, the following result by Sakhnovich is known. If the function P is analytic and the transformation operator exists, then the function Q is also analytic. Of course, it's a very restrictive condition, and so we cannot apply transformation operator method, for example, when these functions are of class L1 in the general case. That's why we will apply another method. Specifically, we will apply the general approach to inverse spectral problems for higher order differential operators, developed by Vyacheslav Anatolievich Yurko and based on the method of spectral mappings. This method works not only for the fourth order, but for higher order operators of the form 5 of any order. Here I provide references. This is one of the first papers of Yurko in this direction of 1989, and this is his book, where you can find the most complete results for higher order differential operators on finite interval and on the half line. But you see that Yurko studied operators of this form with coefficients pk of these Sobolev spaces. So for k greater than 0, they have to be sufficiently smooth. And later on in my papers, in my works, this method was transferred to differential operators with non-smooth coefficients and even distribution coefficients. In particular, you can find some useful results in this paper for distribution coefficients of various singularity orders. Today, I will not elaborate into the topic of distribution coefficients, but strictly speaking, in order to deal with this equation, we have to apply my results for the case when P and Q are L1 functions. But in fact, today we'll talk about uniqueness theorems, and uniqueness theorems and the proofs are not very different from the analogous results of Yurko. So let me formulate some results. For simplicity, we will consider the fourth order, not the general order differential equation, but the fourth order equation of this form 6. Here, I also add first derivatives of y with some coefficients r, which also belongs to L1. These coefficients are not necessarily real valued; they can be complex valued. And to deal with this equation, let us introduce the quasi-derivatives. The quasi-derivatives for g equals 0, 1, and 2 exactly coincide with the usual derivatives, and the third quasi-derivative is defined by this expression. Next, in order to define the boundary conditions, introduce the linear forms US are the linear forms at 0, and VG are the linear forms at 1. We can introduce them in this way, or we can choose some other permutation of the boundary condition orders. For example, like in McLaughlin's problem, it doesn't matter. I just provide the most simple case. Next, we need some solutions of equation 6, denoted by phi k, the solutions of 6, satisfying the boundary conditions 8. For the solution number k, we have k conditions at 0, and for minus k, conditions at 1. Delta is k here is the Kronecker delta. These solutions phi k are called the Weil solutions. Since they are solutions of the boundary value problems, they are meromorphic in lambda for each fixed x, together with the quasi-derivatives. Let us consider the matrix. Actually, it's a fundamental matrix formed of these solutions at x equals 0, and denote it by m of lambda. This matrix is of size 4 by 4, and it's called the Weil-Yurko matrix. The following important theorem holds that the Weil-Yurko matrix uniquely specifies the coefficients of the differential equation 6, P, Q, and R. As I have already mentioned, this is one of the results which for smooth coefficients was proved by Yurko, and for non-smooth coefficients, for L1 coefficients, it follows from my mentioned paper. So the Weil-Yurko matrix is the most important spectral characteristics in this theory. And what is remarkable in this theorem, that there are no restrictions on the spectra of the corresponding boundary value problems. You see, there are no restrictions here. This theorem is valid for any behavior of the spectra. Next, let us consider the properties of this matrix in more detail. It can be easily seen that the Weil-Yurko matrix is the unit lower triangular matrix, and under the main diagonal it has some non-trivial elements. And below there are some formulas provided for these elements. Let us first denote by CK the solutions of our equation, satisfying the initial conditions. US are linear forms at 0, so there are initial conditions, and so these functions are entire in lambda. And then this formula holds for the elements of the Weil-Yurko matrix. Here, delta KK is defined in this way: is a determinant of some matrix which is composed of these entire solutions. So, and delta GK is the analogous determinant which is obtained from delta KK by replacing some CG by CK. So these functions are entire in lambda. So the elements of the Weil-Yurko matrix are meromorphic functions. And also it can be easily shown that the zeros of delta GK coincide with the eigenvalues of some boundary value problems, LGK for equation 6, with the following boundary conditions. For us, the most important problems will be the problems with indices KK, with equal indices KK. For brevity, I denote them by LK. Because the eigenvalues of this problem are the zeros of the determinants. So they are the poles of the elements of the value call matrix. The zeros of delta 1, 1 are the poles for the first column. The zeros of delta 2, 2 are the poles for the elements of the second column. And the zeros of delta 2, 3 are the poles of this element. In fact, if we have all these spectra, then we can construct the corresponding characteristic functions, and we can construct the value co-matrix. So the value co-matrix corresponds to several spectra. Let us count how many spectra there are. There are 3 denominators, and there are 6 numerators. For each element, we have its own numerator. So totally, we have 9 spectra. For order 4, the value co-matrix correspond to 9 spectra, but this is for the general case. Under some additional restrictions, an amount of data for the unique reconstruction of the equation coefficients can be reduced. One of some such conditions is the so-called separation condition. Let us assume that for each k, the neighboring problems Lk and Lk plus 1 have no common eigenvalues. What does it mean? The eigenvalues of Lk are the zeros of the k's column of the while Yurko matrix, and the eigenvalues of Lk plus 1 are the poles of k plus 1's column. So if we assume the separation condition, it means that no 2 neighboring columns, in this case the first column and the second column, and similarly the second column and the third column have no common poles. The problems L1 and L3 can have common eigenvalues, so this is only for neighboring problems. And then under the separation condition, the following result holds. For the unique recovery of P and R, not only for P and Q, but for P, Q, and R, we can specify not the whole value co-matrix, but only 3 elements which are colored by blue here. So we only need the elements under the main diagonal. And these elements will be sufficient for the unique reconstruction of equation, not only for P and Q, but also for R. As far as I know, the separation condition for the first time appeared in the papers by Libenzon, but Libenzon had more restrictions. He also assumed that the eigenvalues of these problems are simple, but if they are not necessarily simple and separation condition holds, this uniqueness theorem was proved by Yurko for the smooth coefficients and in my papers for non-smooth case. Actually, the proof is the same. Next, there is the following question, which is frequently asked. Do there exist such coefficients, such equations that the separation condition holds? Actually, there are many such operators. The first and the most simple example is the case when P, Q, and R are all zeros. In this case, it can be shown that the separation condition holds. Second, recently, I have obtained the characterization of the spectral data for some class of the fourth order differential operators for with coefficients of the spaces. And under some additional conditions, I like Lebenzon assume that the eigenvalues of problems LK are simple. And for this class, the separation condition is also assumed. So there is a complete spectral data characterization for this class. And now I will not discuss this result in details. It published in my paper of this year in the journal Mathematics. And it gives a wide class of using the spectral data characterization, one can construct a wide class of operators which satisfy the separation condition. And moreover, if we have any coefficients P, R, and Q, one can choose a finite perturbation of the spectral data, choose it in a special way so that the separation condition is achieved. So we can actually we can take any problem and modify it so to achieve the separation condition. So there is a wide class of operators satisfying this condition. And so next, let us return to our main problems and first consider Barcelon's problem. For Barcelon's problem by three spectra, theorem 3 was proved by me together with my colleagues from China. We have proved that under the separation condition, the three spectra of Barcelon's problem uniquely specify the coefficients P and Q of equation 3. I'll briefly say about the proof of the theorem. First of all, let us notice that this spectra coincide with the zeros of some characteristic functions. For delta 2,2 and delta 3,2, it's obvious from the definition. For delta 2,4, it requires some technique, but it's rather simple. If we have this spectra, then we can construct the corresponding characteristic functions by using Hadamard's factorization theorem. Here also some constants appear, but these constants, they don't depend on the coefficients P and Q. They depend only on the structure of the boundary conditions, so they are absolute constants and can be easily found. So we have three spectra, then we can find the characteristic functions, and then we can find some elements of the value co-matrix. Let us have a look what elements do we have. We have these red elements of the second column. But I remind you that if we want to apply the uniqueness theorem for the separation condition, we need also the elements M21 and M43. In order to deal with these elements, we need the next lemma 2. This lemma follows from the special structure of our equation and boundary conditions. You see here we don't have the coefficient r at the first derivative. And also the structure of the boundary conditions is chosen in such a way that we get some symmetries in the value co-matrix. In particular, these two blue elements coincide with each other. So actually, we need to prove the uniqueness for at least one of them. And also we obtain such a useful relation 14. Next, denote the eigenvalues of the spectrum S12 by lambda n. And it can be shown that by using this relation and by using the red elements, which already known, we can find the values of the element, say, M21 at the points lambda n. And next, we obtain the following lemma that these values uniquely specify the function M21 for every lambda. This lemma actually based on some, the proof of this lemma is based on some estimates. We have to construct the Behoff type solutions in some sectors, and then estimate the characteristic functions delta gk, then estimate this element, and using this estimate, this uniqueness lemma can be obtained, and so the element M21 is uniquely specified, and then we can apply the result of the general theory, which says that the coefficients P and Q are uniquely recovered from these three elements under the main diagonal. So this is the idea of the proof of so we see that the uniqueness theorem for Barcelon's problem holds under the separation boundary under the separation condition. Next, let us consider McLaughlin's problem, and first of all, we can notice some relationship between Barcelon's and McLaughlin's problems. For McLaughlin's problem, we introduce the linear forms in slightly different way. U1 and U2 are these two linear forms, and U3 and U4 will be the remaining forms of orders 0 and 1. And Vs are introduced similarly to the previous problem. Let us consider Barcelon's problem for spectra SGK, for GK 1, 2, 1, 3, and 2, 3, which are the spectra for equation 3 with the boundary conditions 16 with these new linear forms. So we have fixed boundary conditions at 1, and we have different combinations of boundary conditions at 0. For this choice of the boundary conditions, the same result is weighted that if the separation condition holds, then these three spectra uniquely specify P and Q, and it also can be shown that they specify the constants A, B, and C. And we will use this fact, we will apply this fact to McLaughlin's problem. Recall that the spectrum S12 is exactly the spectrum lambda n of this problem. Gamma n's and xi n's are the norming constants. And it can be shown that under the separation condition, these three spectra uniquely determine McLaughlin's data, the eigenvalues, and two sequences of norming constants, and vice versa. Norming constants are determined up to the signs because here we consider eigenfunctions normalized in this way. If we take minus yn, then it also will be the eigenfunction, but the norming constants change their sign. So here they are defined up to the sign. Of course, the sign can be fixed in some way. So up to the signs, they are uniquely defined by three spectra. Here are exactly the relations. Recall that if we have these three spectra, then we have these three characteristic functions. Moreover, instead of delta 3,2 and delta 4,2, we can equivalently consider only the values at the points lambda n. Using the estimates, it can be shown that they are uniquely interpolated by these values. And then the following relations hold. If we have three spectra, then we have the function delta 2,2. We can find these derivatives. We can find these values. And so from these relations 17, we can find gamma n and xi n up to the sign. On the opposite, if we have gamma n psi n and lambda n. We also can construct delta to 2, find these values, and recover these values of these functions at the points lambda n, and then determine 3 spectra. So we see that this resonance proof theorem 4, and theorem 4 implies theorem 5, that under the separation condition, the spectral data of McLaughlin uniquely specify the coefficients of our problem. But what is interesting, that for McLaughlin's problem, the separation condition is unnecessary for the uniqueness. Let us consider this problem without separation condition by using a slightly different technique. Using our linear forms, define the problems LK as before, and we can, of course, we can define the value co-matrix. Here is how the problems LK are defined. They have these boundary conditions. The case problem has k conditions at 0 and 4 minus k conditions at 1. Anyway, it's technically difficult to consider the general case without the separation condition. So we impose some other technical condition. We will assume that the eigenvalues of L1 and L2 are simple. Actually, the eigenvalues of L3 will coincide with the eigenvalues of L1, and they also will be simple. In this case, the poles of the value comatrix, all the elements of the value comatrix will have simple poles, and the value comatrix in the neighborhood of each pole can be represented by the Lorentz series of this form, with only one term in the main part. Here, these notations m-1, m0, m1, etc. Are used for the 4x4 matrix coefficients, constant matrix coefficients. So this is the matrix formula. And let us, instead of the Y matrix, use some discrete data. We will use its poles and some data associated with these poles. Namely, we will use the weight matrices, which are defined by this formula, by the coefficients of the Lorentz series. So the general theory implies that under the simplicity condition, the discrete spectral data, the eigenvalues of all the 3 problems, and the corresponding weight matrices uniquely specify the desired coefficients. The case of multiple eigenvalues also can be considered, for example, for the second order, for the non-self-adjoint Sturm-Liouville operator. This case was studied by Buterin. And then we have more terms in the Lorentz series and need to work with these terms. But for higher orders, the technique with multiple eigenvalues becomes too complicated, and so we confine ourselves to the simplicity condition and to this discrete data. For McLaughlin's problem, the following theorem can be obtained, that under the simplicity condition, McLaughlin's spectral data uniquely specify the coefficients of the problem. Let me briefly describe the proof of this theorem. Remind that the eigenfunctions yn fulfill these boundary conditions with the linear forms u1, u2, and v1, v2. And if we substitute yn into the forms u3 and v3, there are 4 possible cases. If the separation condition holds, then we always have this first case. For all the eigenvalues, we have this case. But if a separation condition doesn't hold, then we can have different cases for different eigenvalues. the cases 2, 3, and 4 are also possible. And it can be shown that in each case, the weight matrices have different structure, which is presented on the slide. Here, stars mean non-zero elements, and the other elements are zero. Here are the matrices for the case 1, 2, 3, and 4. And we also have such eigenvalues shown that these matrices, all these non-zero elements, are uniquely specified by McLaughlin's data. So McLaughlin's data uniquely specifies the discrete spectral data associated to the singularities of the Weil-Yurko matrix. And this idea proves our uniqueness theorem. And next question is, can we remove the separation condition for Barcelon's problem? But what is surprising that for Barcelon's problem, we cannot remove the separation condition, we cannot omit it. And this is shown by a counterexample. The idea of construction for this counterexample is the following. We choose some specific spectral data, the eigenvalues of 3 problems and the weight matrices. So these are the discrete spectral data corresponding to the Weil-Yurko matrix. And by using this data, we construct functions P and Q by using the method of spectral mappings. And then it is shown that for some specific choice of the spectral data, this example will show the non-uniqueness of Barcelon's problem solution in some special case. So I'll use the following notations. For k1, 2, and 3, lambda and k are the eigenvalues of the corresponding problem Lk. For convenience, the problems L1, L2, the boundary conditions for this problem are presented here. Here I use the simplest boundary conditions of the lowest orders. I don't use these McLaughlin's conditions because in them there are also constants A, B, and C, and they make a construction of a counterexample more complicated. So we constructed for the most simple case, but for this case, it's included into the cases considered in Barcelon's paper. This notation N and K is used for the corresponding weight matrix. And if P and Q are real valued, then it can be easily seen that the problem L2 is self-adjoint, and L1 and L3 are adjoint to each other. Next, how the method of spectral mappings work. For this method, we have to choose some model problem and then consider perturbation of the spectral data for this problem, and then construct some new problem, which will be our counterexample. As we choose the problem with the 0 coefficients as the model problem, so we consider P with tilde and Q with tilde equal 0. Then the corresponding, it can be easily shown that the corresponding eigenvalues of the second problem are simple and positive, and the eigenvalues of the first and the third problem are simple and negative. So the separation condition holds for the model problem. The weight matrices will have this form. For k equals 2, we have this form with only one non-zero element, and N1 and N3 are equal to each other, and they have this form with 2 non-zero elements. And Moreover, it can be shown that the spectra of the first and the third problem coincide with each other, and that these two elements are also equal to each other. And next, by using this data, so this data can be explicitly found because it corresponds to zero coefficients. Then let us consider some perturbation of the data. We perturb only the data for index n equals 1. We consider lambda 1, 1, lambda 1, 2, and lambda 1, 3, that they all be equal to the eigenvalue lambda 1, 2. And the weight matrices will have this form with some positive number gamma at this corner. And all the other data coincide with the data of the model problem. For n greater or equal than 2, the data of our main problem and of the model problem coincide. So we can use this new data to construct some functions p and q. Of course, this fact needs some proof that because the method of spectral mappings reduces the inverse problem to some equation. We have to prove the solvability of this equation, but it is done, and we arrive at the following result. For each positive gamma, there exist unique functions p and q, which are infinitely differentiable, such that equation 3 with the coefficients p and q has exactly this spectral data defined by these formulas. And if we consider the corresponding three spectra of Barcelon's problem, then we can show that they don't depend on the parameter gamma. So by taking different values of parameter gamma, we obtain different p and q, but we have the same three spectra. And the theorem shows the non-uniqueness in this case. So let me conclude the results. First of all, we have proved that under the separation condition, solution of Barcelon's problem is unique. But in general, the solution of Barcelon's problem is non-unique. It is shown by a counterexample. Next, under the separation condition, Barcelon's and McLaughlin's problems are equivalent to each other. For McLaughlin's problem, the uniqueness holds without the separation condition. And the most important conclusion that both these problems can be interpreted within the framework of the general method by spectral mappings. So there are not some specific cases. They can be interpreted in terms of the general theory. And here are the papers. The papers about Barcelon's problem are prepared together with my colleagues from China, Guang and Yang. And also there are two problems about McLaughlin's papers about McLaughlin's problem and counterexample. So my talk is over. Thank you for your attention.
Thank you very much. Please, questions.
I have a question. You discussed the uniqueness of the potentials in your problem, the fourth order. I was wondering if you could get also information on the boundary conditions.
What information do you mean?
I would like to prove, say, that under some spectral information or some data, you can prove that the boundary conditions are unique and eventually to reconstruct them.
Yeah, thank you for this question. In McLaughlin's problem, the coefficients of the boundary condition, it's proved that the coefficients of the boundary conditions are uniquely specified by the spectral data. And actually, in the general approach, I mean in these results, for example, here in these results. I also studied more general cases, and also Professor Vyacheslav Anatolievich Yurko also has studied more general cases when boundary conditions also have some coefficients, and then these coefficients can be recovered. But this complicates the technique, and the recovery will be different for different orders of boundary conditions. For example, for the second order, for the Sturm-Liouville operator, we can have Dirichlet boundary conditions, or Robin boundary conditions, or Dirichlet-Robin boundary conditions, and so the technique will be slightly different. And here there are even more possibilities. But actually, yeah, boundary condition coefficients also can be recovered.
Okay, well, thank you.
More questions?
May I ask you a question which is not directly related with your interesting talk, but somehow, you know, you mentioned that the transformation operators were not efficient for higher order differential equations. My question is about, you know, in the book of Leontiev on generalizations of series of exponentials, in fact, there is a transformation operator which doesn't have such a form of Volterra second kind operator. It's another, but it is clearly a transformation operator which wasn't in fact used anywhere. Have you considered it, or do you know this?
No, I haven't considered these other forms of transformation operators. So maybe Vyacheslav Anatolievich.
Yeah, I can say something.
Yeah, please.
You see, the form of the transformation operator for higher order you mentioned really was constructed by Fage from Novosibirsk. And he was his doctor thesis, second thesis. And since this transformation operator is really, it's really nature, but it doesn't work. And one of the reviewer was Levitan for his, in Russia, for the second thesis, you need 3 opponents. And one of these opponents was Levitan. And Levitan wrote the negative report because this his motivation that this transformation operator cannot be used. And then, after some months, Levitan changed his mind, and he agreed that Fage, it's not the fault of Fage. There is a nature that the transformation operator in general case really has this complicated form. And you see, in my first thesis, I tried to use this transformation operator. And there is one paper, unfortunately not in the good journal, but very some maybe book of the paper, but it's maybe 60 years ago. And I got some uniqueness results for higher order differential operators using namely Fage's transformation operator. But unfortunately, there were several very strong restrictions. And in general case, when no restrictions, as I know, nobody tried to use it because it's very complicated, it really doesn't work. Since this transformation operator method uses the counter in the complex X plane. This means that we automatically need analytical properties of the coefficients. But if we have analytical properties, we don't need this. So situation is the following. Really, such a transformation operator exists, but unfortunately, nobody used it.
In fact, well, I'm not sure that this is the same transformation operator, because yes, it is a counter integral in the complex plane of x, it can be said, but it doesn't require the analyticity of the coefficients. And I mean, no.
Yeah, I agree with you. It doesn't require analyticity. But if you would like to use it for the newest problems, in this case, we can get some results only. You are right that in order to construct the transformation operator by Leontief and by Fage, by the way, it can be reduced each to other, so it's equivalent.
So it's the same, yeah.
It's the same. And really, this transformation operator can be constructed without analyticity properties. But if you want to use it, till now, it's only for analyticity coefficients. But maybe someone in the future will use it, but till now, nobody uses it.
Okay,
Except me.
Thank you.
Except me, but with strong restrictions. So, other questions? So, if not, so let us thank the speaker for the very interesting talk. And now we have 10 minutes break.
Thank you.
Olaf, would you like to try sharing your screen?
Yes, okay. Let me try. Can you see something?
Yes. Are you ready